Hello, so in this video I want to test how emitter degeneration affects the headroom. So what I'm going to do is I'm going to choose my 2N2N2N2222 transistor. Then I'll just put a voltage source to bias, then another voltage source as the microphone. Then I'm going to put a ground here. Press W to wire them up. So the emitter grounded first, and our 1K collector resistor placed here, and our 5 volts VCC. So let me just rename everything VCC 5. I'm going to do 0.68 as my bias voltage. Then the microphone, a sinusoidal, (10 milli) and 1K frequency. Let me call this the mic. And let me call this VBE bias. Okay, so I can only space and leave an underscore. I can move things around to make my work neat. Okay. All right, so this is what we have. Okay, so I'm going to run this, and the stop time 10M, and we see so the voltage, we have the current of 2.5 milli, 2.57. so the voltage output reading from down here, after I subtract 5 and I take 2.57 from 5, that's what I'm going to get as the output. And the swinging because of the so I can just separate the output with the capacitor. So I'll put a capacitor here. Two micro, that's a trick. And I put a very large resistor here to be sort of an open circuit. 1, 2, 3, 4, 5, 6 is enough. Okay, so I'll see the output swing alone. Compare that to the input from the microphone, then you know we have significant output voltage swing. So the 10 millivolt swing is now giving me very huge, about 800. So my gain is about 80 in this circuit. Okay, so what happens to the headroom? So let's go back to the voltage with the DC. I'm resting on 2.3 and I can go down minus 0.8. So there's somehow 1.1, 1.2, so 1.5 or something like that. Let's look at it clearly here. Okay, so I take away the, and up here too I go up plus 0.8 millivolt. That's the swing that I'm getting. Okay, don't know what's happening here, but I think that's my PC giving me issues. Okay, so the headroom with the resistor, now let's assume that there's no okay, let me take this, let me give a value of 0 so it doesn't really change anything. Let me confirm. Yeah, okay, so if the signal here, the voltage here down here is 2.42, so I'm going to cut off the bias voltage and see what happens. So now the operating voltage here, forget about the scope, so just look down here, you see the operating voltage to be 4.999, basically almost 5 volts. So what happens if I put a resistor value here? Why can't I change that? Okay, let me just cut it and put a new resistor there. I don't know what I did wrong there. I'm just going to change that to 100. Of course, there is no current flowing through, so I don't expect this 100 to change anything. I'm going to wire them up and I'm going to have the current flowing through this time around. So I need to run. Okay, so let's see what happens. Now the available voltage now goes to 4.524. So 4.524 with the headroom. So let's see. Okay, so this guy is only consuming just a tiny bit of it. But it's also affecting the gain. So let's see the current here. And the current is 400 and so you know what happens is whenever you put ammeter resistance, it limits the collector current. As the collector current is coming in, the emitter resistance also raises in voltage and reduces the available collector current, because the voltage raised here would also try to oppose the collector current. As the collector current tries to increase, this voltage will also try to reduce the collector current. So ideally the gain reduces significantly, and that's something that we see. So if I go back now, I'm going to put a bypass capacitor here. and I'm going to call this, sorry, 2 micro. So what happens is my AC signal will not see the emitter, and the gain will not be reduced for AC signal. So let me run and see how it goes. So I think I should have my 80 millivolts with a bypass capacitor. Without a bypass capacitor, then my AC gain reduces. So okay, I never ran it, sorry. So after running it without a bypass capacitor, my AC gain has now reduced. So let's see how the emitter resistance also affects the okay, so looking at this, you see with the gain, normal gain, I have A is equal to minus GM RC. But once you bring in the emitter degeneration, the gain now becomes RC negative over 1 over GM. So without emitter degeneration, the GM goes up here and have the same. Emitter degeneration, you put something here. So if 1 over GM is far greater than, sorry, it's far less than RE, then we can approximate our gain to be RC over RE. Okay, and we can see that clearly. But if I use a bypass capacitor, then the AC signal will not see the emitter degeneration. The emitter degeneration will just be seen by the DC current. Let me illustrate that. So without the bypass capacitor, both the AC and the DC current are being affected by the emitter degeneration, and it has its own advantage. From the previous playlist, you will understand what it does. And also, once I connect the bypass capacitor, we see how the AC signal coming in would not see the emitter resistance, but the DC current coming in, we've already explained that the current can be split into a DC component, which corresponds to the bias, and AC component, which is the small signal changes from the signal. So we still have amplification and the benefits of the emitter degeneration, which can be seen if we wanted the bias voltage to be stable. So there's a whole video on that in the other playlist. You can check it out if you are struggling to understand that concept. Okay, also with emitter degeneration, we see that the voltage, midpoint voltage, has been raised. Without the emitter degeneration, the midpoint voltage was quite low. So let me run and look at this. Okay, so the midpoint voltage is now 4.542 with emitter degeneration. Okay, so now if I take out this resistor, I could have just short-circuited it. So let me do that. So let me take it out with a short circuit. So basically it doesn't exist to anyone, both AC and DC, because it's just a short circuit. And I run this, then the midpoint voltage has now come down. But with the emitter degeneration, you can also think of it as the emitter degeneration also increases the output impedance of the whole thing. So that's one way you can look at it. And maybe in the next video I'll really concentrate on the headroom and the emitter degeneration. So for now, bye.